Okay, so let's get started. Lesson 1 is magnetism. Okay, so here we go. We've got natural magnets, we've got artificial magnets, and we've also got these things called electromagnets, which are a really big deal and kind of the whole point of why we have to go through this conversation. But let's work our way towards that. So, first of all, 3 categories or classifications of magnetic materials. Just quickly, because ferromagnetic, that first word you see there, is a term that I will throw out once in a while. So let's just take a look at this. Ferromagnetic, this are metals, this refers to metals that are easily magnetized, and we've got a bit of a list here. We've got iron, nickel, cobalt, and manganese. Okay, drop to the bottom, the third point, diamagnetic. These are either metallic or non-metallic materials that cannot be magnetized. So a piece of driftwood. Okay, you can try till your heart's content, but you're never going to get this thing to take a magnetic charge. The one item that's on this list that is of particular interest is copper. Okay, copper is, of course, our primary conductor. That's what we use to build an electric circuit, not exclusively, but so much of the time. And it is a diamagnetic material. It cannot be magnetized. Something that's really interesting and we take huge advantage of. More about that later. In between, we have this thing called paramagnetic materials, and it's just in between. Okay, some things can be magnetized. Okay, it takes a lot of effort, you know, sort of somewhere in the middle. So it's a sliding scale, ferromagnetic at one end, diamagnetic at the other end, and paramagnetic, kind of all the stuff in the middle. Okay, so just an introduction to some terms, because I will be throwing some of these out here occasionally. Okay. Start out a conversation about natural magnets, naturally occurring rocks referred to as lodestones, and they are magnetized. Just naturally they occur. We can mine these products. Okay, it's unknown exactly what causes them to be magnetized. Some ideas are maybe lightning strikes to ferrite materials, which causes what we would call long-term ordering. Okay, which is essentially a permanent magnet. Now these were used by early explorers to create crude compasses, okay, way back historically. That's what the first compasses were. It was just a piece of naturally occurring magnetic stone. Artificial magnets are anything that we can cause to be magnetized. Okay, so we can break these down into permanent or temporary. So a permanent artificial magnet means that it stays magnetized for a very long time. Okay, and a very long time, we're talking in terms of decades, centuries, eons. Okay, very long time. Okay, only 3 elements are ferromagnetic at room temperature. So there's that term. I told you we were going to see it. Okay, and this list we've already seen: iron, cobalt, nickel. Okay, so these are substances. These are elements that can be magnetized. We call them permanent artificial magnets because for an exceptionally long period of time, once you've applied some kind of energy to magnetize that material, it will remain that way. Okay, all man-made permanent magnets must contain one of these base elements to work. Okay, so any magnet that you've ever encountered will have one of these in it. And the final comment there says most powerful magnets are made from alloys. So this is not a chemistry lesson. We're not going to get into a lot of detail here. Just a little bit. But again, this kind of goes over my head really quickly. So just sort of to build the picture, paint the picture, understand what's going on. This thing called Alnico is a mixture of aluminum, nickel, and cobalt. So there's that list. Okay, useful up to 550 degrees Celsius. So under extremely high temperatures, this alloy will still maintain its magnetic properties. Okay, ceramics, applications under 300 degrees. Okay, they are weaker magnets, hard, brittle. Okay, but resist corrosion. So again, depending on the applications, there's all kinds of reasons why things might be beneficial for one application as opposed to another. Okay, all artificial magnets. Notice it mentions there fridge magnets as an example of a ceramic, potentially. Moving on. See how quickly I'm going? We're getting to the good stuff. It comes later. So those were permanent artificial magnets. Temporary artificial magnets can lose their magnetism or do lose their magnetism fairly quickly. So here it says as soon as they are removed from the magnetizing influence, okay? Probably not immediate, okay, but really fairly quickly. All right, soft irons such as nails or screwdrivers, they can be temporarily magnetized, okay, but you know, over a period of minutes, hours, days, whatever the case may be, the ordering is eliminated and the magnetizing or magnetic component of it is lost. Okay. And then finally, there's a mention here of electromagnets again. They are temporary artificial magnets, but we're going to talk a lot more about them in a little bit. We'll come back to that. That's kind of going fast now to get to the interesting stuff later, and the electromagnets definitely are the interesting conversations. That's really the point that we're working towards. All right, so here we go. In order to understand and quantify a magnetic field, so I've talked in these weird, huge generalities, what is it exactly we're talking about? In order to really understand and talk about what magnetism is, we talk about what we call lines of flux, okay? And lines of flux, also known as flux lines or lines of force, any of those terms referring to the very same thing, okay? Now, we're going to look at these. We're going to draw a whole bunch of pictures drawing lines of flux. Typically, we only draw a couple of lines, all right? 2, maybe 3 lines. That's enough to give us the image to understand what's happening. 1 Weber is equal to 100 million lines of flux. So while we are drawing 2 or 3 of them, there are many more. Okay, so that gives you a little bit of perspective. Okay. One final thought about quantifying magnetic fields. A Weber is just a count, just quite simply how many lines are there? 100 million. Okay. The other unit of measurement that's really important for us, and there's actually a number of different units of measurement, just like, you know, the metric system and the imperial system, there are centimeters and there are feet, you know, 2 completely different units of measurement, 2 completely different numbers that measure the same thing. There are a number of different units of measurement that talk about the density of the flux lines. So not simply a count, not just a question of how many are there, but a question of how many of them are there in a particular amount of space. Okay, so flux density, usually, if you're interested, expressed in Teslas. So a Tesla is the unit of measurement for flux density. Okay, so there's the lesson, there's the information. We are going to spend no time attempting to do the math. We don't need to. We need to understand concepts. Okay, so we're talking about lines of flux. Okay, and we're talking about a whole lot of them, but we're going to draw pictures with only a couple of them. Okay, so let's do exactly that. On to the next slide. So here we are. We've got a couple of bar magnets and we're drawing, you know, groups of 3 lines of flux. Okay, trying to understand how these magnets interact with one another. Okay, so these invisible lines of force of magnetic field called flux lines, they actually form 3-dimensional shells. So all of our pictures, most of our pictures are going to be 2-dimensional. Don't lose sight of the fact that all of this is 3-dimensional. Okay. The other thing is too, I don't know what your background might be. If you've taken lessons about magnetism at a university level, you're probably scoffing at me right now because the concept of lines of flux are considered old and obsolete. Okay, at a much higher level of education than we need to go with this conversation, it's now referred to as a cloud. Okay, we're not going to do that. Okay, the lines of flux are much more beneficial for us to conceptualize and talk about what's happening. So we're going to stick at the level of lines of flux. Okay, we don't need to take this to a serious degree. We simply need to understand concepts. Okay, so the symbol used to represent flux is the Greek letter phi. Moving on, let's understand the behavior of these lines. What we see are some nice round circles. Okay, if there was only a single bar magnet, okay, these circles, they would be nice and symmetrical. Okay, what I want you to recognize from this picture and take away from it is that these lines are not symmetrical. Okay, we have the 2 north poles that are opposing one another, okay, like poles like poles repel, unlike poles attract. Okay, because these two north poles are pushing against each other, okay, we see these arrows here. We see these arrows here showing that there is a repulsion force at work, okay, pushing against each other. And the result is that the lines of flux get a little bit compressed here and they get extended out in this direction. Okay, so there is some reaction happening, and the lines of flux no longer are nice and symmetrical. Okay, they're getting pushed out here on all of these corners. Okay, so there's a reaction taking place that's causing these lines of flux to distort as a result of the interaction of the lines of flux from the two different bar magnets. Okay. Like poles produce a repelling force on these held in place magnets. So we hold these magnets in place, we try to push them together, okay, and they push apart, okay, and the flux loops get distorted as a result of this. All right, do you feel any smarter yet? Not really. 8 characteristics of lines of flux. Okay, you won't find this in the textbook anywhere. Delmar does not articulate the behavior of lines of flux with these 8 points that I have here. But a teacher of mine many years ago made this list, and it does a really, really good job of defining the behavior of magnetic fields. And so I have taught these 8 characteristics for many years following his lead, and it works really well to help explain the behavior of magnetic flux lines and magnetic forces. Okay, so first rule: lines of flux always form closed loops. So in fact, that first slide we looked at, okay, just showed the little tails coming out of the north poles of the magnet. Okay, that was an incomplete picture. Okay, the complete picture would be the next picture we looked at, which showed the loop as a complete loop. Point number 2, these loops never intersect. And there's a point later on that explains why this is true. They travel north to south externally, so I'm sure you noticed that those lines had arrows on them, and those arrows are pointing in a specific direction. What is that direction? North to south. They have tension and length. Well, what does that mean? We'll talk about it when we get to that slide. They take the path of least reluctance. Okay, you probably in the basic electricity probably talked about the concept of current following the path of least resistance. These magnetic lines of flux do a similar thing, the very same thing actually. They follow the path of least reluctance. They go through all things, which means there are no insulators. You cannot put up an insulator or a barrier from magnetic forces. Okay, you may say, well, wait a minute. Yes, I have. Well, we can do something that's similar, but in terms of the behavior, it looks the same. But when we look at the theory about what's actually happening, it's really very different. We'll look at that. And then 7 and 8 talk about parallel lines of flux. And 7 says that parallel lines in the same direction repel, and parallel lines in the opposite direction tend to unite. Okay, they actually turn into a single line of flux. Okay, so there are the 8 characteristics. Let's look at them in more detail. Magnetic lines of flux always form closed loops. So here's a picture, a very simple picture. We have 4 lines of flux. Okay, very often we will only draw the lines of flux outside the magnet, but don't forget the fact that those lines actually go through the bar magnet internally as well. Okay, notice there are some arrows on that, so we'll get to that in a couple of slides, but every single line of flux is a complete loop. Okay, characteristic number 1. Characteristic number 2, they never intersect. So here's our first 3-dimensional picture. Okay, our lines of flux creating a cloud, and they all spread out as symmetrically as possible, and they never cross, they never intersect. Magnetic lines of flux travel north to south externally. So here's the rule when you're putting arrows on these lines of flux. North to south externally, which means, and again, I've already gotten lazy and I haven't done it, if I were to complete this loop and show it coming through the bar magnet, then I could put an arrow on this that goes this way, right? No, I did that wrong. North to south, which means south to north. Sorry about that, guys. South to north goes that way. Scratch that out. I'm going to blame the technology. That's completely because I was fighting with the computer that I made that silly mistake. Everybody completely confused yet? That arrow is going from north to south outside the bar magnet, which means it's going to go from south to north inside the bar magnet. North to south externally. Sorry I made that so difficult. It really shouldn't be. Magnetic lines of flux have tension in length. Now here's an interesting one. I don't have a good picture for this. Okay, you're going to have to create the picture in your mind. Okay, imagine an elastic. And as you stretch the elastic, okay, it wants to return to its former length. Okay, so that is tension in length. As you stretch it, it wants to go back to its original length. All right, that's where the analogy between a magnetic line of flux and an elastic works. That's what the tension in length means. The other thing we have to talk about, though, is the amount of tension. And here the magnetic line of flux is the exact opposite of the elastic. So as we stretch the elastic out further and further, the more we stretch the elastic, the more tension it has, the stronger it is pulling back towards its original length. Okay? Lines of flux are the exact opposite. They offer the most tension. They are the strongest when they are the smallest. Okay, as you stretch those lines of flux, as you pull the two magnets apart, imagine you have two magnets, South Pole and North Pole, and they've sucked themselves together, they've attached, and you are pulling them apart. The greatest tension, the greatest force is when they're closest, and as you move the magnets further and further apart, you have less and less strength in that tension. Okay, so let's think about that point where it breaks. All right, when the elastic breaks, it's very dramatic, okay, because its tension is greatest just at the moment before it finally gives up and breaks. Okay, the lines of flux are the opposite. There is no dramatic moment when those lines of flux finally break. It's a very subtle, unrecognizable moment in time because they are strongest when they're close together, and then that strength fades until it just doesn't exist anymore. Okay, so tension and length. The fifth point, magnetic lines of flux take the path of least reluctance, okay, just as electrical current follows the path of least resistance. I'm not sure that there's much more to say about that, but it leads into a further conversation. Moving on to this one right here. Magnetic lines of flux go through all things, which means there are no insulators. Okay, so what we do, we cannot build a shield, okay, to stop lines of flux. What we do instead is we offer a path of less reluctance to encourage the lines of flux to go in a particular direction. So instead of shielding from those lines of flux, we are actually absorbing those lines of flux. So what I've drawn here is a little picture. We've got a couple lines of flux and this circle or this ring, and imagine you are standing in here. Okay, this is you. This is my artwork for you guys. Whew, you have long legs. There you are. So if this ring wasn't here, these lines of flux would be going straight across a page and straight through you. Okay, if you want to build a quote-unquote shield so that those lines of flux do not go through you, you offer a path around you which has a high permeability. Oh, there's a term we haven't talked about yet. This is a ferromagnetic material, something that is easily magnetized, wants to be magnetized. It will have less reluctance, and the lines of flux will choose to go in that direction, and the lines of flux follow this path through this ferromagnetic material around you. So there's a magnetic shield. Okay, it appears like a shield, it functions like a shield, but when we understand what's actually happening, it's the exact opposite. It's not blocking the lines of flux, it's absorbing them and say, hey, come this way. Okay? And finally, the last two, and these are really the two big ones, okay, in terms of understanding why two bar magnets behave the way they do. Okay, it's all about these parallel lines of flux. So parallel lines in the same direction repel. So this is the very first picture that we saw. Okay, remember that these lines of flux create complete loops. So this actually comes all the way around and back in there. And I can put an arrow there, which is south to north internally. But we don't state it that way. We always talk about north to south externally. So there's an arrow there. Okay, now parallel lines in the same direction repel. So from this bar magnet on the right, we have a parallel line right there pointing up. And from this bar magnet on the left, we have a line right there, which is parallel to the other line, also pointing up. So there are two parallel lines of flux in the same direction, and they push against one another. And that is why two north poles or two south poles, okay, like poles repel. It's because of the behavior of these lines of flux. Okay. The other thing that this characteristic does for us, I promised we would talk about it. So let's go back to the notion of lines of flux never intersecting. This is the reason why. Because within any given magnet, okay, all of the lines of flux all travel north to south externally, which means those lines of flux right there are parallel. And that is the reason that the lines of flux create a cloud. They're all pushing against one another, and so they're all spreading out evenly, and that's why we get that nice uniform cloud around the magnet, because all of those parallel lines in the same direction are repelling against one another. Okay, so there's a few different things that are explained by this very simple rule. Okay, and finally, the last one, the eighth one, says that parallel lines in opposite directions unite. So here we go. We've got two bar magnets that are spread apart. Okay, so north on the left, south on the right, on both of these two bar magnets that we're looking at on the top, and they have these nice uniform lines of flux. Okay, nice uniform loops. But again, let's look at the lines that are parallel. So if I look at this line right here, okay, there is that line of flux with the arrow pointing up. And we come over here, and here's this line of flux, which is parallel to it. Oh, sorry, that's supposed to be a single line. I'm trying to just make it nice and thick. So these two lines are parallel. This one is aiming down. So what we have right there at that point are two lines of flux that are parallel in the opposite direction. Same thing down here. That's going down, and this one is going up. Okay, parallel lines in the same direction. What do? They tend to unite. And the result is, instead of two separate bar magnets with two separate clouds, okay, two separate loops, okay, they become one. And again, not a complete picture, because that's just a very small part of the loop. It carries on through here, and it goes all the way up and around here, and it comes in here, and comes back to there, and there is one complete loop. Okay, this arrow shows the lines of flux traveling from north over here, externally all the way around to south over here. That's a single line of flux, and we can see that they have united. So instead of two separate loops, one around each independent magnet, we have one loop through both magnets. And now we refer back to the rule that says lines of flux have tension and length. There's a long loop, and it's going to try to become a smaller loop and pull those two magnets together. And again, the closer the magnets get together and the smaller that loop becomes, the stronger the force is to continue getting smaller. Okay, so there are the 8 rules of the behaviors of lines of flux which help us to understand what's happening when we look at a magnetic field. Okay, moving on. This video is going to be getting kind of long, I'm afraid, but let's change pace. Time to talk about electromagnets. So that's all the conversation about just magnetism in general, but now let's bring it back to specifically the electromagnet. So the whole conversation of how does magnetism and electricity interact and combine, and why do we even care? Okay, this is a course in electricity, and I just spent the last, probably half an hour talking about magnetism. Why? Well, the answer is right here. Okay, because It's not quite true. I will correct myself later, but essentially you can't have one without the other. Okay, that's really the idea. And certainly in the first direction, which we're looking at here, every time you have an electric current, you will have a magnetic field formed as a result. Okay, it's as simple as that. Whenever electric current flows through a conductor, a magnetic field forms around that conductor. Okay, so it's, I don't know if I want to call it a byproduct, okay, but it's a fact of nature that it's just there, okay? And we use it very much to our advantage. There are lots and lots of examples where we take this and we put it to very good use, okay? This is how electric motors work, all right? It is the force of the magnetic fields that gives us our rotation and our torque in a motor, okay? It's also how, well, you've already taken a course in motor controls, and so you've learned about contactors and relays and motor starters, and they all utilize this right here. Put a current through a conductor, and it creates a magnetic field, and that's what pulls the contacts, either open or closed. Okay, so we take this rule, this basic law of physics, and we put it to very good use. So magnetism and electricity are closely related. Okay, current flow produces a magnetic field each and every time. Okay, the field strength, how strong that magnetic field is, depends on the amount of current and the length of the wire. Okay, both of those are relevant, and that's going to determine how strong a magnetic field we get as a result of the current flow. So we have current, and we know which direction current flows. Okay. And we know that that current is going to create a magnetic field, and we can represent that magnetic field with these things called lines of flux. And we know that we can put arrows on those lines of flux, so there's direction there. So we need to figure out direction. And we have hand rules that we can use. We put our hands to good use to figure out these directions. So the first bullet there says the direction of current flow through a conductor, and the direction of the lines of force can be determined by using either your left or your right hand. Oh, crazy. We can use both hands. The rule says we grasp the conductor in our hand with the thumb pointing in the direction of the current flow, and the fingers will point in the direction of the magnetic force. So I have a picture that shows what that looks like. There it is. There's the conductor. It says the direction of current flow is to the right, and it shows the direction of the lines of force up over the top and down across the back of that conductor. Okay, so there are the lines of flux with arrows. Okay, notice that this picture used the left hand, but I said you could use your right hand as well. What would happen if you grasped that conductor with your right hand? So your thumb still has to point to the right, that's the direction of current flow, but your fingers are now going to come up across the back and down across the front. So we get the other answer. Depending on whether we use our left hand or our right hand, we get opposite answers. So why both hands? What's going on? What's going on is that we have two different theories about the direction of current flow. Okay, the conventional flow theory says that current flows from positive to negative. But the electron flow theory, which represents what's actually happening at the atomic level, and it is the flow of electrons that is current, actually travel from negative to positive because electrons are negatively charged and they're flowing from an area of high concentration to an area of low concentration. So the area of high concentration means that's the negative terminal of the DC power supply. Current flows from that negative terminal to the positive terminal where there are fewer electrons. So the electrons actually flow in that direction. So when we look at that conductor that was in the previous picture, we talked about current flow going to the right. Okay, but were we talking about current flow using the electron flow theory, or were we talking about current flow using the conventional flow theory? Okay, so if we change hands, okay, the right hand says current's flowing that way. Can you guys see this? Yeah. Conventional flow theory says current's going that way. Electron flow theory says current's going that way. And in either case, we get the same answer. The lines of flux are going that way. Okay, so that's the important point here, is the lines of flux are always going to be pointing in the same direction because there's no discrepancy, there's no lack of agreement about the direction of lines of flux. They travel north to south externally, end of conversation. Okay, and so the direction that our fingers point, showing us the lines of flux, will always be the same. But the direction our thumbs are pointing, talking about current flow, will change depending on which theory we use to talk about that current flow. Okay, so here's the rule. Conventional, let me underline this for you. Conventional theory is the right hand, and electron theory is the left hand. Okay, that's the rule. That's how we keep it separate. Conventional theory uses the right hand. Electron flow theory uses the left hand. Okay. So here's a couple of pictures. Let's focus on what's on the left of the slide. We'll deal with what's on the right of the slide in a moment. Actually, no, I'm going to change my mind. Let's look at the two images on the top, left and right. Notice what we're looking at here is a cross-section of a conductor. So we've cut the conductor and we're looking at the end of it. Okay. On the top left, we see a dot, and on the top right, we see a plus sign. What do those images represent? What that's telling us is that is the arrow that's pointing in the direction of current flow. Okay, and the arrow is here, and there's the tip of the arrow, and the back of the arrow has some quills. Okay, so here on the left, the dot, that is the tip of the arrow coming towards us. Okay, so that image in the top left means that the current is flowing out of the computer screen towards us. The plus sign over here in the top right means we are looking at the quills back here at the back of the arrow, which means that current on that conductor is flowing into your computer screen away from you. Okay, so that's what those details tell us. All right, so let me ask you this. Top left, the current is coming out of the computer screen towards you. Which hand do you use to get the lines of flux going clockwise around that conductor like is shown? Okay, so let's do this. Current's coming out towards us, and the lines of flux are going around clockwise. And I'm using my left hand to make that determination. Okay, so that means that this slide was created using the electron flow theory. Okay, or at least that image was. Let's check the other one. Now, if the current is flowing in away from us, the lines of flux are counterclockwise around the conductor, and I still use my left hand to make that work. So it looks like my left hand is probably going to work for the entire page. Electron flow theory. All right. That's a good message when you do all of this work. Once you choose a theory, you've got to stick with it. Okay. Same was true when you did your Ohm's law calculations last term. Right. Once you figure out what theory you're using, you can't decide to change your mind halfway through. Okay, the next two images, if we move down, we're looking at pairs of conductors. Okay, and there's two different scenarios there. The conductors, the pair of conductors here on the left, are two conductors with current flowing in opposite directions. And you can see that you end up with the two separate lines of flux, or sets of lines of flux, if you will, one for each conductor. Because they are opposite in the same direction, they are repelling. You can actually see them pushing outwards. They are considerably distorted as a result of the interaction of the two fields. Okay, what you have here on the right, however, is you have two conductors where current's flowing in the same direction. Because current is flowing in the same direction, the lines of flux in the middle are where they are parallel, are not in the same direction as they were in the example on the left. They're in opposite directions, which means they unite. And what happens is you get a single larger magnetic field created from those two conductors with current flowing in the same direction. Okay? And then at the bottom here, this is just a blown up conductor showing you the current and the lines of flux. You can practice your hand rule with that. Still using your left hand, right? Still using your left hand. Current's going to the left. Lines of flux are coming up over the top and down across the face of that conductor, left hand. Okay, moving on. Remember the slide that said the strength of the magnetic field depends on two things, the amount of current, and the other thing was the length of wire. Okay, so the longer the wire, the more magnetic field you're going to have. Now refer back to something I said much earlier, that when we talk about the strength of a magnetic field, we could talk about it in terms of Webers, which is just a count, or we could talk about it in terms of Tesla, which is flux density. So if we take that much longer wire and we scrunch it up together so that everything is denser, we bring everything together into a smaller space, it magnifies everything. And so we do that by taking the wire and coiling it up. We create a coil. Okay, so this particular coil that you're looking at has 10 loops, which means the strength of the magnetic field created by this coil will be 10 times greater than the conductor all by itself. Okay, and that is all about flux density. We've taken the conductor and the lines of flux around that conductor and squeezed it into a much smaller space. Okay, as a result, you get a much stronger magnetic field. So the fact that we have a magnetic field around a conductor, we don't worry about too much. Okay, conductors are going here, there, and everywhere, and there's a magnetic field around them, but they're pretty weak and nobody cares. Okay, to take advantage of the magnetic field, to create a motor, to create a contactor or a relay somewhere where the current creates a really usable magnetic field, we're going to have to make a coil. Okay, it's all about the coil, because we take that long conductor and we squeeze it into a really tight space. Okay, so let's talk about coils. We have a hand rule for the coil as well, because what happens is you take all of these 10 individual magnetic fields and you bring them all together, okay, and create a single magnetic field. And so there it is. Okay, so this shows the left hand, and here's how we use the left hand rule. Now it's going to be our fingers that are going around in the direction of the current, because the current is now wrapped around this coil, and the thumb points towards the north pole of this electromagnet that we have created. Okay, let's take a closer look with some images. Look at this. You can let's zoom right in on just a single conductor. And we can use the conductor hand rule here. Okay, left hand, current is coming out towards us, which means the lines of flux are going to be going clockwise around that conductor. There and there. Okay, we already looked at what happens when you put two conductors side by side with current flowing in the same direction. They're going to unite. And so all of these lines of flux around all of these conductors from one end to the other are all going to unite. And current's going to be going up there and down there. And what happens when they unite, and you can see the arrows on those images, there's one there, and there's an arrow going through there. So if we now look at the line of flux that's created by this, comes all the way around externally and back around internally. And what do lines of flux do in terms of travel? They travel south to north internally, but what we say is north to south externally. So this coil of wire, when we look at the behavior of the lines of flux, looks exactly like a bar magnet. Hand rule. The magnetic polarity of the coil can be determined by grasping the coil in your hand with the fingers pointing in the direction of current flow. So the fingers are wrapping around the coil pointing in the direction of current flow, and the extended thumb points in the direction of the lines of flux inside the coil. Okay, so inside the coil goes from south to north, which means your thumb is pointing at the North Pole. Okay, so this is the coil hand rule. Same thing is true. We've got two hands, right? Okay, this doesn't happen. This happens. In all cases, our thumb is pointing to the North Pole, but is current flowing this way through that coil of wire or is current flowing this way through that coil of wire? Maybe that's the right answer. Maybe that's the right answer. Okay. Just like the conductor hand rule, when we're using the coil hand rule, the same thing is true. The matching up of the theory in the hand. The conventional theory uses the right hand. The electron flow theory uses the left hand. I'm pretty sure this is my last slide. So let's wrap it up. Electromagnets. An electromagnet is a coil, okay, which has the very same properties as a bar magnet. So here's where the 8 characteristics of lines of flux are so useful, is it explains the behavior of a magnet. And it doesn't matter whether it's a bar magnet, whether it's a permanent artificial magnet, a temporary artificial magnet, whether it's an electromagnet, a coil of wire, those same 8 rules apply. Okay, the beauty of this, and this is going to refer back to something I said way back in the beginning, the beauty of this is that we can turn it on and off. Okay, temporary and permanent artificial magnets mean that you apply some kind of force, creates or causes that ferromagnetic material to become magnetized. You can remove the magnetizing agent and the magnet remains, okay, for a period of time. Very short if it's a temporary magnet, or for a really long period of time if it's a permanent magnet, because they are ferromagnetic materials. If we are creating the magnetic field by using current, and we're putting current through a copper conductor is diamagnetic, which means the material itself, the element, copper, will not become magnetized. So the moment you turn the current off, the magnet goes away. So it's somebody was smart enough to recognize this. Somebody went, hey, this is really helpful. We can put current through copper. We can get a magnetic field as a result of that current, but we have an off switch. Okay, we don't have to wait for that temporary magnet to finally lose its magnetism. As soon as we turn the current off, that's an off switch on our magnet. Okay, so really, really, really beneficial. Okay, final thought here is we can insert a core inside this coil. And if that core is ferromagnetic, it also has the ability to strengthen the magnetic field. Okay, so we have the ability to coil the wire up to strengthen the magnetic field. We have the ability to put more current through that coil to strengthen the magnetic field. We also have the ability to place some ferromagnetic core inside the coil and, again, increase the magnetic field. Okay, what happens here, of course, is that when you remove the current, you still have some lingering magnetism from the core. And the example I'll finish with is in a scrapyard, you have large cranes that move scrap metal from one pile to another using a magnet, okay, using an electromagnet. All right, you set the bar magnet, or the electromagnet rather, you set the magnet down on a pile, you turn the current on, you create the magnet, you lift up the steel, you move to the other pile, and you turn the current off. Now, if you've ever watched this, or watched it on TV and Discovery Channel, whatever, you've probably noticed that typically when the bar magnet, sorry, not the bar magnet, when the electromagnet, the crane, returns to the first pile, there's typically something that's dangling. Okay, the magnet didn't quite turn off. And that is the residual magnetism. That is the temporary artificial magnet not quite demagnetizing. Okay, and that's the core. That is not the copper coil. Okay, I think that's enough for now. I'm going to shut it down. I will put a whole bunch of material on Blackboard. We'll get going on some stuff. There's not a lot of homework at this point. Okay, that's going to come later, I promise. For now, get through my lesson. Go to the Delmar, read the corresponding material that's there, get yourself comfortable with this conversation, because while we won't be doing a lot of testing specifically on this material, we didn't put any time into quantifying any of this. I didn't share with you any equations. There are hundreds of them. I could have gone on for days. This material, the foundation, the understanding of this is going to be required for the duration of the course. Okay, so much of what we do week to week to week to week to week is based on you understanding these fundamental concepts. Okay, so no homework yet, aside from just making sure that you understand this stuff, because it's going to be really important moving forward.